Hello everyone. In this video we will consider the accelerated gradient descent method, which achieves a better performance as compared to the classical gradient descent. For simplicity, we consider the unconstrained minimization problem, x star is equal to arg min over x, f of x, where the function f is L smooth. We know that if we use gradient descent to solve this problem, then we obtain the following bounds. For the convex case, the oracle complexity is order BL by epsilon, and for the strongly convex case, the oracle complexity is order L over mu log 1 over epsilon. However, it turns out that gradient descent is not the best algorithm for these two settings. The accelerated gradient descent proposed by Nesterov in 1983 was shown to improve these oracle complexity bounds and in fact achieved the following rates. For the convex case, it achieved order square root of BL by epsilon, and for the strongly convex case, it achieved order square root of L over mu log 1 over epsilon. The Nesterov's accelerated gradient descent algorithm is a kind of method that makes use of a term which we call momentum. That is a multiple of the difference between consecutive iterates, that is xt minus 1. Within the update equation, it is called momentum because if you imagine xt to be the position of an object at a time t, then xt minus 1 is proportional to its velocity or momentum. To extend this analogy, we are making use of the momentum of this moving object and therefore avoiding very sharp and sudden turns. The exact reason as to why momentum helps in the context of optimization is, however, difficult to grasp. In fact, initially, for some years, even researchers struggled with understanding the geometric intuition behind the acceleration. Though that is no longer the case, and in the last decade, a number of different perspectives have come up. Nesterov proposed the estimate sequences framework, which provides a way to construct this class of optimal algorithms. Before discussing the accelerated gradient descent, let us take a look at some history and in particular Polyak's heavy ball method. First, let us define the mapping t of x equal to x minus eta times gradient f of x. So the classical gradient descent, which uses the iterations xt plus 1 equal to t of xt with eta equal to 1 over L. The momentum idea was first proposed by Polyak and the goal was to avoid the zigzag behavior. The momentum is denoted by dt equal to gamma t of xt minus 1. Polyak proposed the heavy ball method, whose updates are given by xt plus 1 equal to t of xt plus dt, which can be written as xt minus eta times gradient f of xt plus gamma t times xt minus 1. As you can see, the idea behind momentum was for the algorithm to remember the direction in which it was going earlier. So at iteration t, instead of going only along the negative gradient direction, the algorithm takes a step which is a combination of the negative gradient and its previous direction, which is contained in the momentum term. So in many scenarios where the gradient descent exhibited zigzag behavior, the momentum term sought to dampen these oscillations and avoid the zigzag behavior that is characteristic of the gradient descent, thereby speeding up convergence. A caveat, however, is that even though the idea of momentum seems to be intuitive and simple, it is anything but. While the heavy ball method was shown to be better than gradient descent for some problems, its oracle complexity was no better than gradient descent in general. In fact, for strongly convex functions, there is no global convergence guarantee for the heavy ball method, like we have for gradient descent. In other words, it was not known that starting from an arbitrary point, if the heavy ball method would even converge to the optimum or not. So this implies that there is more to momentum than meets the eye in this context of Polyak's heavy ball method. For many years, almost 2 decades, no one knew if it was possible to obtain speed up using momentum. The question was resolved by the Nesterov's accelerated gradient method, whose updates take the form xt plus 1 equal to t of xt plus dt, which can be written as t of xt plus gamma t times xt minus 1, which can again be written as xt plus dt minus eta times gradient of f at xt plus dt. So as you can see, the momentum term is applied to xt before deciding the gradient direction. Actually, another way of writing the update is yt equal to 1 plus gamma t into xt minus gamma t into xt minus 1, and xt plus 1 equal to yt minus eta times gradient of f of yt. Whereas in the gradient descent, we can choose eta to be 1 over L, but the choice of momentum parameter is not as straightforward. One possible choice is gamma t equal to t minus 2 by t plus 1. As we already stated, the Nesterov's accelerated gradient algorithm achieves the oracle complexity of order square root of LB by epsilon. As already mentioned, this is significantly better than the order 1 over epsilon rate achieved by gradient descent. In the proof, we will use a technique of adjusting parameters so as to achieve telescopic sums, as we have done in the context of Frank-Wolf and subgradient methods. However, here the analysis will be longer and more involved. For the sake of simplicity, we will directly set eta equal to 1 over L throughout. The analysis for the general eta case is also very similar, just involves a few more terms that would have to be dropped later. Before getting started, let us introduce some shorthand notation. We will denote delta t as f of xt minus f of x star, which is the optimality gap at iteration t, and gt as minus 1 over L gradient of f at xt plus dt. So with this notation, the update can be written as xt plus 1 equal to xt plus dt plus gt. Also note that dt plus 1 equal to gamma t plus 1 into xt plus 1 minus xt, which is equal to gamma t plus 1 into dt plus gt. So remember that dt plus 1 is proportional to xt plus 1 minus xt and also proportional to dt plus gt. In this case, we will actually obtain two one-step inequalities and then combine them. First, note that from the quadratic upper bound, we have that f of t of x is less than equal to f of x plus gradient f of x comma minus eta gradient f of x plus 1 over 2L gradient f of x norm square, which is less than equal to f of x minus 1 over 2L norm square of gradient f of x. So to obtain the first one-step inequality, we will use this property by replacing x with xt plus dt, so that tx can be replaced with xt plus 1. This yields f of xt plus 1 is less than equal to f of xt plus dt minus 1 over 2L norm square of gradient f of xt plus dt, which can also be written as f of xt plus dt minus L by 2 norm square of gt. Next, we can use the convexity of f to obtain that the f of xt plus 1 is less than equal to f of xt plus inner product of gradient f of xt plus dt comma dt minus L by 2 norm square of gt, which can again be written as f of xt minus L inner product of gt comma dt minus L by 2 norm square of gt. Now subtracting f of x star from both sides and recalling that the optimality gap was given by delta t, we get our first one-step inequality, which is that delta t plus 1 is less than equal to delta t minus L by 2 norm square of gt plus 2 inner product of gt comma dt. The second one-step inequality can be obtained in almost the same way, but this time convexity is applied in a different way. Recall that we had already obtained that f of xt plus 1 is less than equal to f of xt plus dt minus L by 2 norm square of gt. Now at this point we can apply the convexity at x star so as to get f of xt plus 1 is less than equal to f of x star plus inner product of gradient f of xt plus dt, comma xt plus dt minus x star minus L by 2 norm square of gt, which is less than equal to f of x star minus L inner product of gt comma xt plus dt minus x star minus L by 2 norm square of gt. Finally, using our notation for the optimality gap, we get that delta t plus 1 is less than equal to minus L by 2 times norm square of gt plus 2 times inner product of gt comma xt plus dt minus x star. So if we have both our one-step inequalities, and you can see that we have used both convexity and smoothness, and we would actually not need to use any of them later in the rest of the proof. The required result would follow simply from properly combining these two inequalities. So thus far we have two inequalities, but we do not know how to combine them in order to get the desired result. So just summarizing, we have the inequalities that delta t plus 1 is less than equal to delta t minus L by 2 norm square of gt plus 2 inner product of gt comma dt, and delta t plus 1 is less than equal to minus L by 2 norm square of gt plus 2 times inner product of gt comma xt plus dt minus x star. If you recall, in order to carry out the telescopic sum, we would generally need a relationship which is of the form that delta t plus 1 is less than equal to 1 minus beta t into delta t plus ct, and the rate will be determined by ct and beta t. So here we do not know the value of beta t we would have to have. To get this form, observe that we can take a convex combination of these two inequalities. That is, if we multiply the second inequality by beta t and the first inequality by 1 minus beta t, where beta t is something that is between 0 and 1, then we would obtain that delta t plus 1 minus 1 minus beta t delta t is less than equal to minus L by 2 norm square of gt minus L inner product of gt comma dt plus beta t times xt minus x star. Next, we need to manipulate the term on the right so that it can be telescopically summed. For this purpose, we will use the formula that norm square of u plus 2 times inner product of u comma v can be written as u plus v norm square minus norm square of v. So therefore, the right hand side is less than equal to L by 2 norm square of dt plus beta t into xt minus x star minus L by 2 norm square of gt plus dt plus beta t xt minus x star. Now towards getting the required telescopic sum, we need to carefully look at the right hand side. We really want the last term to be expressed in terms of quantities that depend on t plus 1. To that end, we will use the fact that gt plus dt plus beta t times xt minus x star is equal to 1 minus beta t divided by gamma t plus 1 into dt plus 1 plus beta t times xt plus 1 minus x star, which yields the recursion delta t plus 1 minus beta t delta t is less than equal to L by 2 norm square of dt plus beta t times xt minus x star minus L by 2 norm square of 1 minus beta t by gamma t plus 1 into dt plus 1 plus beta t times xt plus 1 minus x star. Now we are at the final step. We just need to multiply both sides by a term that allows us to carry out this telescopic sum. Of course, in addition to that, we would also need to specify beta and gamma sequences. So let us multiply both sides by 1 over beta t square. Then we have that 1 over beta t square into delta t plus 1 minus 1 by beta t square minus 1 by beta t into delta t, which is less than equal to L over 2 norm square of dt by beta t plus xt minus x star minus L by 2 norm square of 1 minus beta t by gamma t plus 1 into beta t dt plus 1 plus xt plus 1 minus x star. Now looking at this form, it can be seen that the telescopic sum is possible if we choose beta and gamma such that 1 by beta t square is equal to 1 by beta t plus 1 square minus 1 over beta t plus 1 and 1 minus beta t by gamma t plus 1 by beta t is equal to 1 over beta t plus 1. So that is the final requirement. If such a choice is possible, then we are done and we would get the required result. Solving these inequalities, we obtain that delta t plus 1 is equal to 2 beta t divided by beta t plus square root of beta t square plus 4. So gamma t plus 1 is equal to beta t plus 1 times 1 minus beta t divided by beta t. These conditions are in fact possible. One way to see is simply to plot beta t against t and deduce that it is decreasing over 2 over t plus 1. You can also see that 2 by beta t plus 1 minus 2 by beta t is equal to 1 plus square root of 1 plus 4 by beta t square minus square root of 4 by beta t square, which is always greater than 1. So if we start with beta t equal to 1, we would get beta t is less than equal to 2 over t plus 1. The final oracle complexity can be obtained by carrying out the telescopic sum, which yields delta t is less than equal to L times x1 minus x star norm square divided by 2 times beta of capital T minus 1 square less than equal to order of 2lb by t square. So if we equate this to epsilon, we can see that oracle complexity is given by order of square root of lb by epsilon. That concludes the proof. In summary, this proof was relatively simple and involved writing down two one-step inequalities, then taking their convex combination using some unspecified parameters, and finally adjusting the parameters so as to ensure that the telescopic sum is viable. So that is all for this video. In the next video, we will look at the strongly convex case, for which we will try to obtain a contraction based instead of a telescopic sum based bound.